Good afternoon, colleagues. On behalf of the Vice Chancellor and Principal, Professor Nana Poku, it gives me great pleasure to welcome you to the inaugural lecture of Professor Ignatius Nsahlai. The Vice Chancellor conveys his congratulations and best wishes to Professor Nsahlai. Inaugural lectures form part of the university's public lecture series and may only be presented by newly appointed full professors who have been appointed in academic schools and centers. Inaugural lectures present an opportunity for showcasing the exciting and groundbreaking research and teaching being carried out by professors in our university. Each lecture represents a significant milestone in an academic's career, providing official recognition of their promotion or appointment to full professorship. These lectures are furthermore an ideal opportunity for new professors to introduce themselves and to present an overview of their own contribution to their field to academic peers, students, and research collaborators. Inaugural lectures are also a platform for celebrating a professor's academic achievements with his or her family, friends, mentors, and colleagues. I would like to acknowledge the following guests: members of the executive management, members of Senate, our inaugural this afternoon, Professor Ignatius Nsahlai, family and friends of Professor Nsahlai, academics and professional staff, students, guests from Fiji National University, Malawi Institute of Management, University of Pretoria, University of Fort Hare, alumni and distinguished guests. It is my pleasure to introduce our Dean and Head of School, Professor Fatu Mixwell Mudau, who will now formally introduce the inaugurant, Professor Nsahlai.
Professor Ignatius Verla is a professor in the discipline of animal and poultry science. After completing a secondary school education in Nyasoso and the higher school studies in CC, ATS, Bambili, he proceeded into the University of Yaoundé in Cameroon, where he studied natural science, specializing in zoology for the first degree. On completion, he was immediately accepted to register for postgraduate diploma in animal physiology, which he completed in 1985. Upon qualification, he was granted a Cameroon government scholarship into the University of Reading, UK, where he studied animal production, qualifying with a postgraduate diploma in animal production in 1987, and a PhD in animal science in 1991. Upon leaving University of Reading, he served as a food analyst for farmers in Typhoid Reading for 3 months and was awarded 2-year postdoctoral fellowship in then International Livestock Center for Africa, which eventually became known as an International Livestock Research Institute. He was raised to a position of an associate scientist in the same institute for a period of 2.5 years, following which he joined now defunct University of Natal in July 1996 as a senior lecturer, which is now known as University of KwaZulu-Natal. In 2001, he took a sabbatical leave to the American Institute of Gold Research at Langston in Oklahoma, USA. He was later promoted to a level of associate professor in 2007 and to the level of full professor in animal science in 2021. Together with his teaching involvement, he has served as the National Research Foundation Evaluation Panel in 2006 and 2008, National NRF Selection Committee in 2006, reviewers in CGIAR challenges programs in water and food proposals, mentor and facilitator of Sub-Saharan Africa Challenge Program, sub-editor of Animal Science, the Journal of South African Animal Science, reviewer of the United States, Israel, Bionational Agricultural Institute and Development Project proposals. He also reviewed a number of journals and also NRF reviewers for funding proposals and promotions documents. And he also served as an external examiner of programs and theses for universities in Southern region. He has supervised 17 PhDs and 30 MSc graduates, and has published 3 manuals, 6 book chapters, and 138 refereed journals articles, and 71 conference proceedings. He was last rated by NRF as a C1 scientist in South Africa. Against his name, he has an H index of 35 with citations of 3,650. Professor Ignatius Nsahlai is a highly recognized as a research scientist, a teacher in livestock production science globally. You can now present your inaugural lecture to the audience. I thank you. You are now on the stage. You are muted.
Prof, please unmute.
Okay. Is it okay now?
Yes, Prof, we can hear you.
Okay. Yeah, I say I captioned the talk as seemingly seamless, because when you travel and you pass through where livestock are feeding, it doesn't really make a difference. You only see the animals eating endlessly. However, we will go through the talk just now, and we'll see what is actually seamless as suggested. Now, I want to do something strange. I dedicate, as a dedication of this talk, I dedicate it to Almighty God for Him giving me the privilege to be able to be here now. And to my wife, because in her absence, I may not have had the chance to stand here to give any inaugural lecture at all. So I thank her sincerely for from the bottom of my heart. And so we should all be thankful to her, because in her absence, I will not be here to give this lecture today. Now, intake of nutrients by animals, generally in various forms, can eat a roughage and so on. But what we as scientists perhaps try to do to look at the rumen metabolism, we want to know what's happening in the rumen. We want to look at nutrient utilization and anti-nutritional factors. We also look at animal metabolism and utilization. And also intake of nutrients from particularly roughage diets by ruminants. Now, in these areas, that's where I have worked. However, today I will show just a little bit of what I have done. In the process, I developed methods for evaluation and also for detecting anti-nutritional factors. Now, so those publications are there. If you go through my publication, this is what I have been able to achieve. Now let's come back to the real issue. As background, we have animals. The animals, they're influenced by lots of things. And if you look at the scheme of affairs, you find the desired level of production is a response you get from a genetic animal. It has a desire to respond. But because of the various things that are disturbing, you will not see that response. And so the actual level of production will be smaller. And I just made this to depict that kind of behavior, because you start from a bigger one to a smaller one, and that's what we are looking for. Now, I think somebody asked me earlier to use this, and I thought I would, yeah. Okay, now in the discussion today, I say intake of nutrients from particularly roughage diets by ruminants. And there are a set of things I want to deal with. I will look at the digestible organic matter requirement of animals, the empirical model for predicting methane production. Because methane is actually a component of the energy that the animal gets from the food, and that energy is lost. And then you have a total united feeding derivative as a way of determining the digestible organic matter. Because in organic matter, we expect the energy to be locked up in there. And from there, we'll look at the empirical model for predicting intake, and of course, a simulation of intake as well. And this is going to send us to think a little about some of the issues. Now, nutrients of interest, particularly we say energy, with protein will be either NDS, which is nitrogen, the nutrient detergent solubles, or NDF, with the nutrient detergent fiber, whichever you choose. The good part with the NDS, the part that's a little to digest with the NDF. So that's what that implies. In metabolism in metabolism, energy is actually broken down to various components until it becomes net. And in our feed, we can say we have our gross energy, and this is the breakdown process. But I'm showing you this because we will talk a little bit about digestible energy and methane energy here now. So digestible energy is actually now a proxy for it is the digestible organic matter intake. That's what we'll be talking about in a moment. When I started working in Ethiopia, the desire was for us to develop simple methodology that will be used all over Africa. That was the whole thing, what ILCA was doing, and what IRI continue to do today. Based on that, there was a project in which I had to make a contribution, and my contribution was to develop this digestible organic matter requirement for an Ethiopian mainship. It is just the Ethiopian mainship is just like a model in this development process. And now I will help you to understand some of the things. So here it gives you more like the basic requirement, and this component of the model, it gives you the amount over an excess, the maintenance of the animal. So you say on this hand, I'm looking at maintenance, and on this part I'm looking at an amount over and above the maintenance. I don't want to bore you so much on what is written there. So we collected a set of data that we use for this particular process, and you can see the contributors to their work that the data was used. And of course, we developed a set of models, but our interest would be with the fifth one, because it's the one we will choose for simulation as the best simulation. And we, of course, once a model has been developed and you think you are going to use, you have to analyze that model to see whether it's going to work or not. So in principle, we then went through the problem of looking at whether we can use this or not. Look at residuals. You'll find it has residuals that range from 15 to minus 15 to 15. And then you see the behavior of the residua around the predicted digestible organic matter intake. Now, what do these residual tell us? It doesn't show any direction of flow. If it shows any clear indication that it's going a particular direction, then this model will not work. And that's just the fundamental. The second thing we're looking at, MAF is a neutral agriculture, fishery and food. They develop systems, their own system which they use in the UK. We tested against this system. And one thing that does show here that this is an animal in Africa, particularly in the highland region, that is gaining weight. And this is another one that's gaining weight, but the animals differ slightly. This is 25 kilogram animal, and this is a 15 kilogram animal. And so this differential is important. And so in this particular respect, it tells us that the requirement for energy for animals in the African context, it increases quite drastically based on the food we give to animals. Okay, and you can see for 15 kilograms, it also lower than the anticipated. Now, if you look at that's the model. If you look at that, the response to the model, because this is unseen data that was never seen in the development. We use the data that was not seen. What is the dark points here seem to give you an indication of animals that were losing weight. And this, of course, were animals that were gaining weight. And all of them sit on the same line, which implies that the model is actually working. Now, but here there's a problem or an indication from the model, because you can see some stars here, and that those stars are coming from animals from the hot regions in humid areas of Africa. So, which suggests that the animal could be gaining weight with less energy than anticipated. So that is perhaps one thing we can just try to make a quick remarks on. So the proposed model that we predict, the proposed model for predicting digestible organic matter requirement for sheep we've suggested this to be used. I don't know how many people use it. Also, it suggests that animals from hot, humid tropics may have decreased maintenance needs, or they may actually have a better efficiency of gain, not written on the slide. And it applies well to unseen data, because the data that you saw presented is unseen. And that's one thing we concluded. But now we can ask the question, can organic matter of grazing ruminants be also estimated? Now we can go in the next slide, this particular slide. We did a study where we were trying to look at the digestible organic matter of grazing animals. And that's what I'm trying to give to you people today. And perhaps in a caption, I say it's a goodness of outliers. That is one thing that would tell you that the outliers are perhaps good. Yeah? Now, but let's look at what's happened in the rumen first that makes us to think of using purine derivatives. Okay. If we look at this diagram, it shows that feed undergoes rumen breakdown, and from rumen the breakdown of purine derivatives, almost all of this is destroyed here and resynthesized into microbia. And the microbia is what enters into this pool. And once it enters into that pool, it of course will either get recycled, salvaged, which means it's being used for synthesis, or it ends up as derivatives is wasted, and we find it in urine. So if we know this component, then we can be able to say, if we were to get only this portion, we can be able to say how much microbes were synthesized in the rumen, and then we can be able to use that to predict the digestive organic matter that was consumed. Urinary purine derivatives respond rapidly to the supply of the general purine bases at the post-luminal gulf. And we also know that urinary purine derivatives can be used to predict digestible nutrient. We say digestive organic matter intake. So those are some of the what we're trying to pursue, and these are just a methodology. There's no need for us to waste time looking at the methodology, going through experimental procedures. These are the guides that we use in this particular exercise, and these are some of the observations. Of course, here we have organic matter, we have digestible organic matter, and you'll find the differences are quite big. But that's not the key issue. We are looking at being able to predict the digestible organic matter in spot urine sampling. That's our main concern. Now, urine is of course determined the amounts that were excreted by animals. We have total purine derivatives. You can see that there were some differences, and microbia and nitrogen are synthesized, also very different. Where it got a little bit challenging was when we start looking at spot sampling. When do you take the sampling? We see even the total purine derivatives, it has some kind of correlation with it. Oh, sorry. It has some kind of correlation with it. But when you look at the relationship with the digestible organic matter intake, there's nothing you can pick out of here. No indication. So the prediction of digestible organic matter intake, the approach was that traditionally the approach would be to assume that urinary purine derivatives will increase with feed quality, and also assume that creatinine excretion when expressed based on metabolic weight will be invariant. So is that, and with that you can then correct the volume of urine produced. That was what we thought. Now, in reality, you look at the behavior of the cow. The behavior does not look particularly attractive, which shows a lot of outliers. If you were to consider outlier, you don't know whether to take the line going this way or to take the line going this way, or which way to take the line, because these are too many outliers in this whole system. Now, shortcomings of the traditional approach is based on a convenient assumption. We've made assumptions and we believe the assumption and we're happy with it. Convenient, yes, that's one thing. The second thing is multiple outlying points and we cannot ignore them. And so outlying points are not linked to any known cause. We cannot say why the values are lying where they are. So can we then conclude on this work? Maybe it looks difficult to conclude. So it is thus possible that the approach needs to be redesigned in order to overcome the problem of outlying points. That is certainly, this will allow a researcher to continue doing his work. That's basically what we are trying to do here. Now, we know that animals feed on males. They feed, I mean, they have a way they feed which depict their male feeding system. There's a lag period that precedes the onset of digestion. In every consumption, there's a lag phase. Now, the period that elapses between synthesis of microbial matter and urinary excretion also is another period. So we are actually dealing with a complicated situation here. So if we are to look at it, strictly speaking, this is the way it would behave, deal with the behavior over a daily cycle. And so we cannot expect to just predict it clinically and get the results correct. So we need a lot of tools really to work on this. Now, the nutrients and water are consumed to meet metabolic needs. That's number one thing, we know that. And in addition, water intake is modulated by the osmolarity factors inherent in feed. For instance, NDS will be something that would modulate water consumption. Now, if we are to look at the responses the animal have, say it's also these are counterbalancing, because the water intake it positive effect on passage rate and microprotein synthesis. The more the water flow through the room, the more microbes are taken out and the higher the microbial efficiency. That is accepted and it's a known concept. Also, it adversely affects urinary output. So the animal will also output a lot of urine with low feeding derivatives. So the excretion, the concentration of the excretion will not be as good as anticipated. And that then introduced us to a different set of problems. So intake in a feed is proportional to purine derivatives in spot urine sample if and only if water intake and micturition are invariant. That's you expect the animal to urinate, that the urination will be the same, will be invariant. Now, the relationship between them could be strongly positive if collection period is lagged appropriately after feed consumption, and that's certainly true. For the assumption, again, water is available at all times, but that's one assumption that is difficult to make in the context of grazing animals. And urinary output is a correlate of water intake. So mathematically, we will have a function that looks something like this. I don't worry. That is the nature of the function. That you want to determine how much water intake has been taken. Now, we did that, and using this procedure, we were able to capture the water intake of the animal appropriately, because you can see the behavior of the observed urinary output put against the predicted urinary output, which was certainly fantastic for us. Now, the next thing, we already know water input, so are we going to be able to say anything about the digestible organic matter intake on the same data that we looked at before? Now, these are the possible kinds of models that we will have. So we use this model to predict the intake, and our observation was that we streamlined the intake. So digestible organic matter intake, according to this equation, we were able to account for 90% of the variation in the digestible organic matter intake of food. So indeed, what we started with as outliers, we have theoretically, we have placed them in a fashion that will be able to predict the digestible organic matter intake adequately. So this was produced for the sake of giving the African continent a way of predicting the intake of animals that are grazing. Of course, it has some of its nuances. And we realize that we can be able to do that. Some remarks, though. Salvage processes of purine derivatives and the recycling of purine derivatives to the rumen may increase as the feed quality deteriorates. We are not certain. Also, salvage processes of purine derivatives could deteriorate with stage of maturity. As the animal matures, the salvage process could deteriorate with changes in the physical state of the animal and with changes in the physical state of the animal. And lastly, regional specificity of the model is also a problem, which, I mean, what is, I say regional specificity, we did this in Ethiopia. If you are to come South Africa and you want the same response, you must be able to deal with it and do the same analysis here to use the model. Some remarks: the approach based on correcting urine volume using creatinine is weak and thus questionable, and thus of questionable reliability. Okay, and then the proposed approach is simple, fairly stable, and less costly to implement, yet allows for more room for improvement. Now, in a similar fashion, we also developed some other models which can be used by whoever wants to use them. And these are some of them are in these papers that are listed there. But our main question now is, since methane is part of our energy expectation, can methane be predicted? We've seen that we can, let us say how much digestible organic matter the animal needs. We can predict how much for grazing animal. The next question really is whether we can be able to estimate methane that is emitted, because in livestock system, particularly today, people are talking of a serious problem with methane emissions. And animals are always blamed. But I can assure you, it is not the animal. Okay, let's just look at this first. Blackster and Clapperton, they first of all gave us an equation, which was this equation was developed as far back as 1965, and this is the equation. Fantastic and working. Now, the DM, what you find in this equation called DM, is digestibility measured at a level of feeding, which is a maintenance level of feeding. And LM, of course, is we say level of feeding in multiples of maintenance. And this equation were two equations developed together and then of course added together to give you what we are seeing here. Fantastic. And it's been used for some time. So our immediate reaction was to use this model of Blackster. We used it and we had values which we could, of course, run with it. But we realized the digestibility was measured when you feed the animal at the level of in multiples of maintenance. So you must make sure the animal reaches maintenance if you are going to measure digestibility. That is the whole piece of work for me to think of reanalyzing the data. I will say that for anybody who is interested, he can talk to me later and I will explain the details to you. The detail which I perceive was that our methane production in animal should be viewed based on where it begins from and what happens to it, and also some of the things that happen as a consequence of the diet. Now, so what is this methane at zero? It's when you view it, you can say it's methane that is produced in the infinite level of production of methane in an animal, so long as the feed stays in the rumen for extensive length of time. That's what it should represent. Now, the ln is the level of feeding, which is not in multiples of maintenance, but is in multiples of the reticular rumen capacity. So the question you ask, how will capacity of the rumen be determined? Of course, a proxy is given here. That's a proxy with which I worked. And then, of course, after that, we then use the fat, the ether extract, and then, of course, an estimate from it. Now, let's not worry about what these other parameters are doing. Anybody who wants to know details can then ask me about them. Now, this is, in this section, these are estimators of this and KL. The estimators are always 1, 2, 3, 4, 5, 6 items. And we estimated them properly using various givens. Okay, once we estimated them, our main interest is to look at how much of variation we are able to account for in this estimation. And you see, we can account for 75% of methane emission, 79% of methane emission, and account for 74% with respect to KL. Now, those are parameters which we are going to use in our model. And we are happy with this. Because of course, that's the only data we had access to. Now, when we now predict the methane emission, we want to measure if what we have done is actually working. How do you check that? You make sure the intercept is 0, the slope is 1, and this is as high as possible. That's what you are doing. So you say, this is 0, the slope is equals to 1, and this is as high as possible. That is how you look at it in a crude sense. That's the way you look at it. Look at in a Black-Swan and Kaplan model, it's negative, significantly negative, and the slope is significantly higher than 1. Of course, at 0.06, we could explain 61% of the variation. This is fantastic. I mean, this model was developed, these guys collected the data and did all this work themselves. So it's a fantastic piece of work from Black-Swan and Kaplan. And so it's not to say that they did a wonderful piece of job. But alternative, if you were to look at the alternative, it is better because the alternative has simply varied the level of feeding and the way digestibility is determined. That's all. And because you say it does not differ, of course, we are saying that it does not differ from 0, this 1. The slope is not different from 1. And the R square is 80%, which means you are explaining 20% more than what Clapperton's work was able to initially would on its own determine 20% more variation. So this is a better model to use. When you say like that, of course, you have to, in the second piece of work, you want to make sure that there are no correlations. So the correlation should actually be like this one, 0. Yeah, the observed, you find in Clapperton had a very high correlation, the LM moderate, nothing more, and the DM high. In our alternative, we've given you 40.44, maybe slightly less than one of the Clapperton, and this one comes with level of feeding, it comes with not. So in principle, our models, even our models still needs working. And we're saying that if we work it well, and this becomes zero, then that's perfect. Now, what are remarks? Our proposed model is simple, founded on level of field related to rumen capacity, and also we use non-rumen fermentation principle. It is better related is better related to the one suggested by Baxter and Clapperton. So we offer you again a simple thing here for making a proxy to rumen field, and then of course that methane emission will decrease by about 1.337 kilojoules per gram of ether extract in your feed. Now, these are the models that have been developed based on similar principles that we've seen ahead, we've seen above. All these. So you want to follow them up, you are most welcome. Now, diet formulation is, of course, with diet, what we're doing was you have realized that we've started to look at a diet for a particular set of animals. And here we are coming closer and closer to very animals that are indoors. When you are formulating a diet for animals, all these parameters must be placed in the whatever they are supposed to give must be achieved. And then you validate it. Whatever is being done in this table, you validate it with the requirements that the animal need, and also the limits in their consumption. And you'll find that I highlight some here. But our main interest today will be on the intake. So how can we measure or predict intake of roughages by ruminants? Well, we started, we use a different methodology, modificated strategy, which I'm going to show you now, and simulation strategy for predicting intake. In the modification strategy, you have various factors. You will begin with a set of animals, and then operate the model based on the given set of animals. And it's not, now it implies if you start the lowest weight with this, as the animal is growing, you will also use when the animal is grown, this equation for whichever animal. So, but this is a starting point, how to start from an animal learning to eat. Number two, there's a correction factor for the basa. What are the types of basa? And then, of course, in the correction, you have form, is it dry or is it wet, and so on. Maybe you have improved it by treatment, or maybe coming from intercropping, those kind of variables. So these are what defines the basa. Then, of course, there are the environmental factors, and then we have the animal factors, sorry. And after the animal factor, we have a supplementary factor. And so we worked on this model. Now, this is a source of data. This is the data that we use in making sure calibrate the model. And this portion is all the ones I've just passed over there, those are estimation. We don't need to go to estimation. Let's go to the model themselves. What did we find? We end up with one of the best models for predicting a voluntary roughage intake and dry matter intake by ruminants, which could account for 76 to 77% of the variation. That's this model, of course, I will point to you, it has some limitations. Okay. Now, the remarks here, the raw intake model is fairly accurate and it could account for 70 to 77% of variation. Unfortunately, the model is empirical and will require data in each location to calibrate it. For instance, if we are to take this model from the Ethiopian context, wherever it goes, we need data to calibrate the model for the people to use it there. Otherwise, it will not work. That is another thing. So you say for the Ethiopian highlands, it will work for the Ethiopian highlands. Okay, so, and there are a few things because we are one developing. We found that there's one we could not capture was the interaction between roughage quality and upgrading method. Number two, the effect of pregnancy and lactation on the response to supplementation, we could not capture that. And of course, compensatory effect after periods of undernourishment, we failed to capture it, which implies this needs to be done if one wants to use the model. That then sent us again to look for a better model for prediction of intake. And that's where when I can say when I saw the model by Ilios and Gordon, I thought it was most appropriate. Now, let's just get to it. Now, this is what we are trying to do. Now, and for this model, we say the objective was to evaluate the suitability of it. It is good enough a model for us to use and look at where its parameters, because it can be a good model with poor parameters. So we of course, we then went to pick its model and realize the model also requires very low input, because these are all the items that are input in the model to give you the response. And it is sufficiently generalized. That's one thing that's important. It's sufficiently generalized and can be used across all ruminants. It has given reasonable response with limited number of temperate forages. That's one thing that we know. Now, this is a model, and I don't want you to get hooked onto this. Ignore it, and let's go ahead. So we looked at a set of data in the tropical environment a lot, because we had a lot of data, so it was very good for us. We analyzed the data, and here are the results. Now, if you look at this picture, it doesn't give anything good at all. Relationship between observer and predicted digestibility doesn't appear good at all. So, and you say the model by every indication underestimates digestibility values. Now, and we started believing that we had very poor estimate of the KP, which KP is the rate of passage of particulate matter through the rumen. Number two, it could also be due to the model ignores the influence of feed quality on KP, which is true, because they never accounted for this for feed quality, and also the problem associated with rate of digestion was there. And so we got nothing out of this exercise. Okay, So that's, and when you analyze the residual, you find the residual, although it has some inclination, you have to look at it carefully, you see some kind of inclination of going up as you move from this side to this side. Some kind of inclination that way. But it's not very big. So it's not really a problem. Although it would be a problem when you have gotten something, a result that you want to reduce that. We also look at the consumption, the intake. And the model, again, on the estimated intake, for most roughages that elicited high intakes, this behavior, again, not giving us anything better. So poor estimates of rumen diameter load and KP from the rumen could be the reason, or model does not account for the possible interaction between the feed quality, animal productivity, and the environment. Okay, and there's an issue which is based on fixed male allocation. Now, we are not worried about this. Let's carry on. A plot of the residual against observed, maybe this is more like a line set up, something where you don't expect to see any result. This then gives us the line. So, and which tells us that our model, yes, may not it's not working properly. But we, of course, tentative remarks. The model in its present specification is rather one suitable for predicting ruminant intake and digestive autopical roughages. Number two, there is a need to evaluate to evaluate how feed attributes interact with animal and the environment to influence allometric parameters which we use in the model. Number two, we need to reevaluate aspects of meal initiation and termination. These were the major things we came out from this exercise with. Of course, so when we reach this point, we say we should then check our data and rerun the model to see whether the model will give us anything. So we found a new set of data, did a new estimation, and this is the behavior of the estimation. You realize we didn't have a data that will clearly cover the whole of the space. We used whatever was here and whatever was there to do that initially. And then we look for other feeds, and we look at the rate of passage and so on, and we determine how to predict the rate of passage. And here we are not saying our model is very good. We just say it gives us something we can work with, which is better than what we had before. Basically, that's it. And when we have done this, we then we put all this model, we then use this to calculate our rumen load and to calculate our rate of passage, and we put it into the model second time. Now you'll be surprised. The new simulations did give us something. Now, if you look at this simulation, you have nothing better, at least something good, something good, something good, well, equal. And then if you come here on this side, close to, almost, well, it's slightly better than that. And this is much better. Now, this based on the changes, that only two things that we changed. We were able to account for 49% of variation in intake and 32% of variation in digestibility. This is not good enough. We can say that. So both rate and digestion of large particles, both rates of passage and digestion of large particles, and both rates of passage and digestion are largely properties of feeds. Number two, but the rumen load is affected by animal and feed factors. Modified particulate rate of passage and rumen load would increase our precision substantially. So consequently, we felt that we should collect more data to augment this model. That's why a lot of my students have recently worked on this issue. Moyo, I think this Moyo here, you have Adebayo. They recently on passage rate on rumen feed, on rumen feed, on particularly on feeding behavior to sort out some of these issues. Now, this has been done. Some of this work have been done and published, and we are waiting to retest the model. Has the research been seamless? Well, I would like to, the guy who introduced me in this kind of work was Mike Bryant from University of Reading. And after him, I worked in ILCA. Well, we say with colleagues in ILCA, called ERI, we call ILCA ERI now. And I can remember Pascal Osuji, Victor Umona, exciting Nigerian guys who were very passionate about the work we did while I was in Ethiopia, with people like Mike Bonsi, some students with whom I work, Mike Bonsi and Abule Ebro, and so on. These guys were people we did work with. And then we can, at UKZN, even there are lots of people I can name from ERI. And in UKZN, lots of guys here, but there was a mathematician guy with whom I worked, Joseph Apalo, who was fantastic, and he gave us a very good advice and assistance in working out some of these models. And then Langston is where I did my postdoctoral fellowship, my visiting scholar work in the UK, in the US, because that's in Langston. We certainly had good working relations there, and in Halifax, in Canada, this in the University of Halifax. Those are where I have my collaborators. PhD students, around 18 of them, or slightly more, and the MSc, well over 30 students that I supervised. And you imagine working with this group of people, you need to discuss, challenge, and so on. When somebody say the research is seamless, it's not saying exactly what it is. It is beyond being seamless. It appears that it was it seemed was, I said, what I say, it appears it was seemed seamlessly. It was, when you say something is seamlessly, you are saying that it has sealed beyond a point at which a person can open. So in essence, our work, perhaps we were not able to do all of it, because the work was seen, the intake of room that was seen seamlessly. And that brings us toward the end. I want to thank my family, of course, my collaborators, people with whom I worked before, for their contribution in my life. I want to thank my family, particularly my kids, for them being there when I came home. Of course, my wife is obvious. She's the one who has made this possible today. And I thank you all for listening.
Thank you very much, Professor Nsahlai. As someone who has known you for decades, I was touched when you said you thank the Almighty for being here today and able to present this lecture. Many of us know that it was long overdue. And I'm sure many of the colleagues who are listening to you now can attest to the quality of the work that you have produced over the years, and you continue to do so. To our pleasant surprise, as your colleagues at the University of KwaZulu-Natal, the members of your family, your collaborators, and many people who knew you from the beginning of this illustrious career until now, as someone who is resilient. As the University of KwaZulu-Natal, we thank you very much for continuing to do this good work and publishing it on behalf of our university. And we thank your collaborators for making sure that it has happened. I would like to re-emphasize the gratitude of this university to your family and all the work that they've done to make this man successful. I thank the colleagues in the School of Agricultural, Earth and Environmental Sciences who work with you, your students who must be smiling beautifully wherever they are. Many of them are listening to us now. The colleagues who joined us from all over the world to listen to you. And of course, the Office of the Registrar and Corporate Relations at the University of KwaZulu-Natal for working very hard, but seamlessly to make this day happen. And colleagues, please join me in congratulating this man and wishing him all the best in his future life as the Professor of Animal Science at the University of KwaZulu-Natal. Thank you.
Thank you, Prof. Thank you very much.